First of all, we have to calculate the endpoint. This is 0, 0. Of course, this point is going to be 1, obviously. You set the two equations equal to each other. Solve for x. 0 and 1. Okay? So, we have two functions, right? So, the above one, think of like f of x. The below one, think of g of x. So, we have pretty much calculate three integrals. The first one is called my, which is integral from 0 to 1 x times f of x minus g of x dx. And then we're going to calculate mx, which is integral from 0 to 1, 1/2 outside f of x squared minus g of x squared dx. And then we're going to calculate the last one, m. This is the book of R. Oh, a, I mean, it's a because it's not m. Yes, you have to multiply by the density to get m. So, a here is a stands for area, yeah? Integral from 0 to 1, f of x minus g of x dx. Okay? And you take the fraction. X bar is my over a, and then y bar is mx over a. My means momentum around the y-axis. Okay? And mx means momentum about the x-axis. Okay. So, we're going to calculate one thing at a time. Start with my. My is integral from 0 to 1 x. F of x is y equal to x, right? It's f of x. And then g of x is y equal to x squared. So this is x minus x squared dx. And I'll let you calculate this for yourself. Okay? And then mx is 1/2 outside integral from 0 to 1. F of x squared is x squared minus g of x squared is going to be x to the 4th, and then dx. Okay, f of x is equal to x, and g of x equal to x squared. So f of x squared is x squared, and g of x squared is x to the 4th. And then this one is very easy to calculate for Calc 2 students. I'll let you do it. And then a is right here, integral from 0 to 1, f of x minus g of x minus x squared dx. Okay, so you calculate three integrals right here, and you make two fractions. My over a is going to be x bar, and mx over a is going to have y bar. Okay, and you should have the answer. And very similar for other functions. But the integral, the calculation may be more complicated. Depends on the function, but this is the idea. Okay. Now let me move on to another application, the hydrostatic force. Okay. So the idea for this part right here, hydrostatic force, is this. Say you have a container of liquid, usually in our applications water, okay? And you're gonna immerse a plate, say a plate of metal, I just ran the trial, deep into the water. And what happened? Some hydrostatic force, the force of the water, going to apply into the surface of the plate. And you see what? If the region is closer to the surface of the water right here, then the force is going to be less. The pressure is going to be less. Okay, pressure is force over area. And then if the point right here is lower, deeper into the water, then we're going to feel that the force in there is going to be stronger. Okay, so the question is, how much force total applying to that place of water, let's say metal, but who cares, anything, okay? And that place a piece of thing that we immerse into the liquid. And again, in here they say water. A different liquid going to have different density. And in here it's just water. Okay. And the book give you guys a lot of explanation, but let me summarize it for you, make it short. The force in general is calculated by rho times g times d times a. And let me explain one thing at a time. Rho here is the density. Excuse me for a second. right? And G is the acceleration due to gravity. Acceleration due to gravity. Okay? And D here is the depth. Okay? And A here is the area. Okay. So the force applying to the piece of metal, the plate right here, depends on four things. The density of that liquid, gravity, those in our case right here in count two, those are constant. Okay? And D here the depth, how deep did you put that plate into the water? And A is the area of that plate. Okay, so really two things that you're going to worry about is D and A. The depth and the area. Okay. So let me show you. This is how I usually, when I take physics, this is how I used to take care of the problem. Assuming that one more time, the density of that piece of metal right here is going to be identical. It's going to be rho here as a constant. All right. If not, then you have to move into the integral. Okay. So if you have a nice shape. If you're able to find the center of mass, say if I know the center of mass of that, then I can calculate the depth. This is how deep it is. This is D that I want to know. And this is the area. If you know the area of the plate, you know the depth, then you can apply the formula. Rho is a constant given, G is a constant given, and here water rho I think is 1,000. Was that right? Let me double check because is that water? Yeah, that's 1,000 kilogram per cubic meter. Okay, because many times in here we use pounds and foot, so we're going to make sure that. And then G, I think it's 9.8. I think 9.8 meter per second square. Of course, the depth going to be in terms of meter and area is terms of meter square. Okay, all the units going to match up. And then you know the depth, you know the area. All you have to do is multiply. You don't need to do integrals at all. You have the answer. Okay. So let me give you an example. Actually, an exercise in the book. First problem, problem number 3. Water, and I have a rectangular plate this way. Okay, so we have, this is 3 feet. Oh boy, it's feet, okay. 3 feet. The height is 8 feet. And the width here is 2 feet. Okay? And we have the formula force is equal to rho times G times B times A. Okay, so I can avoid calculus by, first of all, find the center of mass right here. It's going to be in the middle. All right, this is 8 feet, so it's in the middle. So from here to here, it's going to be 4. Because I cross the 2 diagonals, I'm going to find the center right here. 4. So the depth is going to be 7 feet. How do I know 7 feet? This is 3, this is 4, so the depth is 7 feet. And what about the area? The area is going to be 2 times 8, so it's going to be 16 square feet. Okay. And if you're using metric, so make sure that you convert everything into meters and seconds, and then you're going to plug into the formula. Or you may find rho and G in terms of feet and pounds, and you have the answer. Okay. I don't have the constant on top of my head right here, so but that's the idea already. Rho is a constant. Let me look for the constant in terms of pound feet. This we have it. I couldn't find it in here. But anyway, you have to convert into meter, 7 feet into how many meters? Okay, meters, and then area into meter square, and then plug into the formula where rho is 1,000 and g is 9.8. I don't feel very comfortable with pound feet, so usually I'll change it back to meters and seconds, and I can do it second for time and minute for length. Okay, but our problem is 3 feet, 8 feet. So usually when I put the problem in the exam, I'll change to like 3 meters, 8 meters, and 2 meters, and everything is just back to the normal language to me. Okay? Say, what if you don't know how to find the center of mass of that thing? You don't know how to find the centroid. So let me change the problem, okay? I'll change this. This one is 3 meters. This is 8 meters, and this is 2 meters. So I don't have to worry about feet anymore. Okay? What if I don't know how to find a centroid? Or what if the shape is kind of strange? How can I still find a static force applied to it? Okay, things gonna get a little bit trickier, and now you have to use calculus. The very first thing that you need to do is to set up a coordinate system. Okay, it's up to you. Choose anywhere you like. So I'll choose right here as the center. And this is my y-axis. And this is my x-axis. Okay. I choose the center right here. This is what I got. So 0, 0 right here. This point is going to be 3. This point is going to be 2. See, 2. Okay, 3. This point is going to be 11. See how I get 11? 3 plus 8 is going to be 11. Okay? And I erase the formula with something. F is equal to rho times G times D times A, right? The first two letters are constant. We don't have to worry. And what about the D and A? So you want to calculate the force applied to the metal plates. The idea is the same as before. We want to chop it up into many horizontal little slices, and we're going to calculate the force applied to that little slice only. Because what? The deeper you move, say down here, that horizontal plate right here gonna get more force because it's deeper to the water. Just calculate the force applied to one horizontal slide. We add all the forces together, we have a total force. Okay, so if you chop it up right here, this is x from the origin. Since I choose the origin right on the surface of the water, the depth d is the same as x. Okay, this is x. And this is also D. Okay? And what about the area? The area is what? And this is a rectangle, so what? Length times the width. So area is length times the width. The length is always 2, and the width is dx, so 2 times dx. Alright? So the little force that apply into that little black slice right here is rho times G times x times 2 dx. So the total force applying to the whole plate is going to be the sums of all the little force, which is rho g is a constant. I'm going to bring it down. Integral 2 is also a constant. I'm bring it down, and I got x dx inside. And you ask yourself, what x run from where to where? Run from here to here. What? 3 to 11. And you integrate this. You have the answer. Okay, so in metric system, rho is 1,000 for water and g is 9.8. Okay. Now, let me redo the same problem. This time I want you a different coordinate system. You guys can see what happened. Let me redraw the picture right here. Okay, this is surface of water. This is the object, okay? And the distance from here to here is still 3 meters. This is 8 and this is 2. Now watch me. I'm going to choose the origins of my coordinate system right here. Okay, so this is my y-axis and this is my x-axis. Okay, so the point right here is going to be at -3. The point right here is going to be 0. The point right here is going to be 8. Okay. So I will chop the same way. This one right here. Now from here to here is x. X, right? X is the distance. is the position of the slide you chop, not the distance. The position right here. So x. What is the depth now? D, the depth. It's not x anymore because x is only from here to here. The depth now is what? The distance from the bar all the way to the surface is going to be x plus 3. Okay? And the area is going to be the same. It's equal to length times the width is 2 dx. dx is the thickness of that bar. This is dx. Okay? So the total force is still pretty much the same formulas. Rho integral times g, right? Integral of d times a. D now is x plus 3, and a now is 2 dx. I can bring the 2 out as a constant and dx right here. Now you see, it's x plus 3 dx. This is x dx. When I claim it, you guys can have the same answer. Why? Because x now is not running from 3 to 11 anymore. In the near system, I choose the origin right here. X is going to run from 0 to 8, right? It's in here. X 0 to 8, and x plus 3. X run from 3 to 11, x dx. See, 0 right here, you got 3 dx. 8 right here, you got 11 dx. It's exactly the same thing. All right. So the key part in here is what? 2 things. You got the formula to start with, okay? And the idea is to chop it up to many slices and then figure out the depth and the area, okay? And I show you the shortcut if the plate is simple enough, nice enough, and you are able to find the centroid, the center of mass, and all you have to do is rho times g, calculate the depth from the center of mass to the surface of water, of the liquid, and calculate the area of the object. You can avoid calculus. All right, let me move on, give you another example. Okay, I'll choose another one that's more complicated. See how we take care of it. Okay, see what we have in here. All right, let's see a triangle now. We have container water, and we have triangle inside. Okay, this way, and this is say 2 feet in the book. Let me change to 2 meters. Okay, and this is 5 meters, and this is 10 meters. So you see that you have a right triangle with a measurement that way. And question asks you, find the hydrostatic force applied to that plate if you immerse into water that way. All right. So I see that with this problem I can cheat. Not cheating. I'm just find a shortcut to get to the answer. I can find the center of mass. Find the center. It's right here. Okay. And I can measure the height. Center is going to be 230. Oh, it's geometry. Okay. You can find the center. Assuming that we don't have much of geometry background, and you don't know how to find a centroid or center of mass, and you have to use calculus. Let's do calculus. That's what the book wants us to do. I'll do calculus. Okay? So how do we take care of the problem? First of all, we have to choose the coordinate system. Where do you want to put the origin? Say I want to put the origin right here. And usually it's easy to put it on the surface of the water, so the depth going to be the same as x. Okay? This is a y-axis. I put it that way. This is my x-axis. I put it this way. Okay? If the origin is right here, so this point is at 2. This one is going to be at 7 because 2 plus 5 is 7. Okay. This point right here is at 10, right? Okay. And then we want to calculate what? The hydrostatic force applied to every single bar that you have on that plate. Okay. So you chop it up into many, many bars. You calculate the force applied to each bar. The difference between this example and the previous one is what? The length of the bars is not constant anymore. It's going to change. So if the more you move down, if you move that bar down to the water, the more you move down, and what? The length of the bar is going to be longer. Okay, it means that a lot more force is going to apply to it. So if I call that position right here is x, change from 2 to 7, right? X right here. Then I will try to find a way to calculate the length depends on x. Now we really have to use some geometry in here. Okay, I got what? This is 10 right here, and this is 5 right here, and I have the bar right here. I don't know what it is, I'll call it y. Okay. X is a distance from here to here, right? So from here to here it's going to be x minus 2. Yeah. 2 is right here, this is 2. From here to here is 2, from here to here is x, so the distance is what? X minus 2 right here. Okay. Alright. That distance right here is x minus 2. So I can use similar triangles I have, but this little triangle right here gonna be similar to the bigger triangle. The bigger triangle, the ratio was what? 5 out of 10, right? 5 right here. 5 out of 10. Gonna be equal to x minus 2 over y. 5 out of 10 is 1/2. Okay. This side over this side will be equal to this side over that side because the two triangles are similar. So they are proportional. Okay. So we can calculate for y right here. Y equal to 2 times x minus 2. Cross multiplication. Y times 1 equal to x times x minus 2. So that slide right here gonna be, the L right here gonna be 2 times x minus 2. Okay? We can apply it to our problem. What? The hydrostatic force is rho times g times d times a, and the depth is x, and the area is the length times the width, which is 2 times x minus 2 times dx. X the distance, okay? And this is dx. Right, dx. Okay, so the total force is rho times g integral. The depth is x, and then the area is, I got a 2 as a constant, I'll bring it out. X minus 2 dx, and x went from 2 to 7. 2 to 7. And you calculate this integral, should have the hydrostatic force total. Okay, now let me repeat the same problem one more time. But this time I will choose different origin, okay, and a position, different position. See how we calculate. Just the same problem, and I bet you calculate the two integrals, you have the same answer. To show you another way to look at the problem. All right, right here, this is my triangle right here. Okay, this time I'm going to choose the origin right at the top. Okay, and this is my y-axis, and this is my x-axis. Okay, so this point is going to be at -2 because the distance from the surface water to that tip is 2. Okay, and this is 0 right here, so this point right here going to be 5. Or this point right here going to be 10. Okay, same idea. We have to jump it up into many little bars. So x is that much. Okay. So the depth is not x anymore. That's going to be x plus 2 because the depth is the distance from the bar all the way to the surface of the water. It's x plus 2. But my triangle now, x is from here to here, right? So if this is x, this is the length L, or that length is that little bar right here. So I got x over L is going to equal to 5 out of 10. Which is 1/2. So L is equal to 2x. The length is 2x. Okay. The previous example, the L is what? 2 times x minus 2. You choose the origin right here, the length is going to be 2x. So the area is going to be the length, which is 2x, times dx, which is the thickness of that bar right there. Okay. So the total force is going to be rho g as a constant integral. What? D times A, the depth is now x plus 2, and A is 2x dx, 2 is a constant, I bring it down, x dx, okay? Now x not going to vary from 2 to 7 anymore. It's going to change from 0 to 5. And arc length, this integral is very simple to integrate. And arc length is both ways have the same answer. Okay? X plus 2 times x, here it's x times x minus 2. X from 2 to